The aim of today's lecture is to learn how to use the SimEvents toolbox within a Simulink environment in the MATLAB software. We will translate the Petri Nets for the preceding week into a new format that will be a simulation model. Thanks to this simulation model, we will get some important information and numerical results about how our process behaves a long time. So the contents for today's lecture will be how to deal with probability density functions in Simulink. And these probability density functions will be used in a Simulink model. But this Simulink model will be focused on discrete event systems. And the toolbox that allows the use of these discrete event systems is the SimEvents, simulation events. This SimEvents toolbox uses block statistics, resources, and probability density functions in general. And obviously, the state of the system will change depending on the events on the system. Finally, the laboratory work will be the dining philosopher's problem, but translated into this new toolbox that will be SimEvents. First of all, when you open Simulink in MATLAB, you can see all the toolboxes that you have installed. As you can see here, I have only Simulink and some small toolboxes in here. And as you can see, I have highlighted the SimEvents toolbox. This SimEvents toolbox is very important because we will be focused in this toolbox during all the laboratory sessions, okay? As you can see here, when you double click on the SimEvents, there will appear a lot of blocks, as you can see here. And I ask for your attention in this highlighted box in here. This will be the legacy blocks. These legacy blocks will be like a small toolbox within this SimEvents toolbox that use some kind of old-fashioned blocks, okay? I strongly prefer to use these legacy blocks within our work in the laboratory because these blocks are very intuitive, as you will see later on. These blocks are the new versions of the legacy blocks, but I'm really interested in this legacy, these old-fashioned blocks, as you will see. If you double-click in this legacy block library, you will see that it opens this new sub-library that is composed by these generators, the sinks, the attributes. I will explain every sub-library in here thoroughly later, okay? The queues, very important, the queues in SimEvents, okay? As you may remember, the queue of the incoming patients at the hospital, for example, the queues in the cash section in a supermarket, the queues in a toll road, in a highway, okay? Then we have the servers routing these entities, the gates. I will explain the gates on the next session, not today's session, next session. Signal management, the entity management. You have some demonstrations in here. If you double click here, you will find some interesting demonstrations from the manufacturer, from MathWorks. Then you have the gateways. Gateways will be very important later on because you are keen now at this moment on timed signals. Your simulations in Simulink are over time. So you have something like this. You have the access time and the signals happens all along this time. But from now on, we have events. Remember, this course is focused on events. The problem of the events is that events happen at discrete times, as you may remember. That's why we explain that we name this kind of processes discrete event system, okay? Because the events that will change the state of the system will happen, sorry, at some discrete times. Here it can happen an event, then here, but events happen not continuously on time, but it depends on probability density functions, as you remember, and events happen at some specific time. Not They are not forced to happen in a continuous form over time. So that's why we need some blocks called gateways that will change a timed signal in here into this. Here we will have the gateway, and this gateway will turn this timed signal into an event signal, and the other way round. We will have gateways that will turn event-based signals into timed signals, because we will be expected to connect timed simulations with event-based simulations. So this block will be very important. This sublibrary will be very important. Then we have the timing library. You will see later on, I will include some timers in my simulation. And finally, pods and subsystems, because sometimes in order not to have a big diagram, I will reduce the size of my diagram by means of subsystems that need ports in order to connect with the external parts of the diagram. I will explain the first elements of SimEvent simulation with the example we have checked the preceding lecture. Remember, sharing on the preceding lecture it was a calculator, now it's a computer, okay? So two students, okay, is Peter, here we have Peter, and here we have Mary. As you can see, Peter is not a good student, okay? He's worried about the results, but Mary is very proud of his A+ results, okay? So Mary is a good student. That's very important because Peter spends a small amount of time studying, okay? But Peter spends a lot of time using the computer in order to do the calculations. So Peter behaves a small time thinking about what to do and a lot of time just trying and having some errors when he's doing calculations. Okay, so the idea is that Peter is a bad student. Peter is always using the computer because he is not sure about what to do. So he is always applying the trial and error method. That's the general idea. While Mary is behaving just the other way round than Peter. Mary is always preparing what to do. She is always thinking on what's the calculations that is expected to be done, okay? So Mary spends a lot of time thinking and writing down all the reasonings for the calculations, and afterwards, when she's quite sure that she needs to do some calculations, she takes the computer in order to do these calculations. So because Mary is very sure on what to do, Mary spends a small time doing calculations. So this transition behave the other way around. Behave One here is a probability density function with a small time, because Peter spends a small time studying, thinking about what to do, while Peter spends a lot of time doing calculations because he's doing the trial and error. So this transition has a probability density function with big numbers in here. So a lot of time, that is Peter spending this time doing calculations, while Mary is the other way around, spends a lot of time here studying, but a small time here in this transition doing calculations. Okay, so that's the general idea. Now I'm going to show you how to translate this problem, this Petri net, into a SimEvents diagram. The important thing is that here we have conflict about a single resource, because these calculations must be done, as you may remember, with the single computer they share. Okay, so Peter will be blocking the computer, will be always, most of the time, using the computer, and Mary will be most of the time waiting for Peter to leave the computer being idle. So that's the general idea. But we need to put numbers in here. We need to get some statistics, okay? So the important thing that you will learn on today's lecture will be how to get some statistics from a simulation. Because if we have some statistics, we can take some decisions on the conflict. That's the general idea, okay? How to focus, how to face conflicts, how to tackle with this problem, okay? When you have some statistics, some numbers that are the basis of your decision, okay? So this is the block diagram about the sharing the computer example, okay? At the beginning, there is, there are a lot of blocks in here, so you may feel overwhelmed, but I will explain step by step this block diagram. Afterwards, I'm going to show you how they can be configured within the SimEvents environment, okay? But first of all, I will explain only the role for every block in this block diagram. Well, first of all, here we have Mary, okay? That's Mary behavior in orange in here. And here at the bottom of the figure, we have Peter, okay? In green, in dark green, okay? That's the difference. But as you can see, it's like a copy and paste, as you can see. This is a copy of all this structure. So if we understand how this top structure has been built, you will understand how this bottom structure has been built, okay? So, well, first of all, now it's only a simple explanation. Later on, I will explain thoroughly every block, how I have configured every block, and so on, okay? But first of all, here we have the generation of Mary. Well, Mary at the beginning needs to be created in the simulation. Now you must understand that we will have events, okay, within our system, but we also have entities, okay? Entities. The entities are the tokens. You remember, when we have here a Petri net, these are the tokens. You remember the tokens that will be flowing all along our simulation system, okay? So these tokens now will be called entities. So Mary and Peter are entities. These entities or tokens they are synonyms, okay? These entities will flow all along the system, okay? And the flowing all along the system of these entities will be managed by means of the events on the system, okay? So the two main ideas at the beginning will be the entities will be the objects, the objects of the people, okay, that is moving, the customers in a shop, okay, the patients at the hospital, the cars that are entering at all. So the entities will be the objects or the people that will flow all along the system. At the end, entities are the tokens in a Petri net. And the events will be the changes in the state of the system. And remember, these changes in the system, these events, will obey on random numbers, okay? Will obey on probability density functions. So that's why here you will find that random numbers will be placed in some sections in my simulation model, okay? So first of all, the general idea is that Mary will be generated in here. So I have a Mary flowing all along the system. And here, Peter will be generated in the system, okay? I will explain you later how I generate Mary and how I generate Peter in my simulation model, okay? But now let's suppose that here we have Mary, and Mary enters this block. This block is a path combiner block. This is only like if Mary goes to the end of the process. If you want Mary to repeat all the process, you need to feed back Mary to the process. This is not this, okay? This is not a comparison, okay? No, absolutely not. This is only a path combiner. Is that like if you have one road in here, another road, they have a common point, and then you have this, okay? You can come from this road, and then once you have finished, you connect again to the beginning like this, okay? That's a path combiner. You go from this path at the beginning, and then when you have finished this path, you can go back by means of this connection, okay? So that's the aim of this path combiner. It's a very simple block, okay? Entities can come from here or from here. So because a single Mary has been created, only a single Mary, then Mary is flowing through this, then Mary reaches the end of the simulation model, and then Mary goes back here, okay? That's the general idea. And the same goes for Peter, okay? Fine. Then here we have this block is the block we call the server block, okay? Server block. Here, Mary is studying. So you must feel this like a place in a Petri net, okay? Mary is studying. That's the process. The time that Mary spends studying, okay? So this time for Mary studying will depend on some probability density function, okay? So that's why here we have a random number generator, okay? But that's not a simple random number generator. This random number generator will be event-based. You remember that previously I have talked about these gateways. You remember? In a simulation model, we have timed signals and event signals, okay? So this probability density function in here, this random number, will get out a value, okay? a number in here when a new entity arrives. Okay, that's the general idea. If you put a random number, a simple random number, a random number will take a lot of numbers in here depending on the simulation time. But an event-based random number will take a random number in here when Mary arrives to this block, to the Mary studying block. That's the difference between a random number block and an event-based random number. Then, once Mary has finished the studying process, then Mary will go to the doing calculations process. You remember? Let's go back to the Petri Net. Here we have Mary studying. And depending on time, Mary can switch to Mary doing calculations. But in order to Mary go or switch to Mary doing calculations, Mary needs the computer to be idle, okay? Mary needs the computer to be idle. So that's why here we have the resource acquire block. Here, Mary will ask for the computer. If the computer is idle, Mary will go to doing calculations process, okay? That's the same structure than before, but this time will be the time, the probability density function for Mary doing the calculations, okay? So Mary will go from studying to Mary doing calculations if and only if the calculator is idle. If the calculator is not idle, Mary will wait here. Okay, Mary will wait here for the calculator to be idle, because we have a big probability that Peter will be using the calculator, okay? So it seems that Mary will be waiting for the calculator to be idle, for the computer to be idle in here, okay? So the general idea is that Mary here will be studying. At any time, depending on this probability density function, Mary will be out of this block, okay? Later on, I will explain the timer, okay? But now, go to the next orange block. This is the resource acquire. If the computer is idle, Mary will take the computer and both they will enter to the Mary doing calculations, okay? And once Mary has finished doing calculations, she will release the resource, okay? So the resource will be idle and Mary will go back to the studying process. And this loop will be repeated forever and ever during the simulation time, okay? So the general idea is that Mary, in order to switch from studying to doing calculations, she needs the calculator, well, the computer, to be idle. That's the reason why this resource acquire block is placed here between the Mary studying process and the Mary doing calculations. The question is, why do I have placed the start timer block and the read timer block? Because here I start literally the timer. That means that when Mary gets out of the studying process, the timer is set to 0, okay? And then if the calculator is available, the time that Mary will spend from here to here will be 0, will be such an immediate process. So the read timer will measure 0 seconds, 0 minutes. That's the idea. But if Mary is waiting here for the computer to be idle, then the time will be running and running and running until the computer will be idle, and then Mary will get out of this queue in here, and then we will stop the timer and read the timer. So the time will not be 0. So the time value read in here will be the time that Mary will be waiting for the calculations. So the time that Mary will be waiting for the computer. That's the general idea. And then once Mary has finished these calculations, Mary goes back to the beginning of the process. That's the general idea for this orange block diagram. As you can see here, I get some information. I will explain you on the second part of this class, okay, of this session, okay? But now I want you to be focused on this resource pool. The calculator, the computer, is defined here. Here I define that there is a single resource called computer that will be the resource that Mary and Peter need in order to switch to doing calculations, to switch from studying to doing calculations. So that's why here I monitor the time this computer is being used. So that's why here I get the percentage of use of this computer. So that's the general idea of this block diagram. So now let's open the simulation model here in the MATLAB environment in order to explain thoroughly what's behind every single block, okay? So as you can see, you have in the virtual campus this sharing the computer Simulink extended file, okay? So at the end, if you drag and drop this simulation model in here, you have the simulation model in your screen. Well, as you may remember, with the mouse wheel, if you go forward with your mouse wheel, you can, as you can see, you can zoom in, and then if you go back with your mouse wheel, you can zoom out, okay? At any moment, you can fit your simulation model with the space bar of your keyboard, okay? If you press the space bar, as you can hear, here you have the model fit to your window, okay? So at any moment, I will zoom in, zoom out, and then I will press the space bar, okay? Important thing, if you press the mouse wheel, there is a hand in here, as you can see, and you can move all along the block diagram, okay? So if you, for example, are here and you wanna move to another section, you can press the mouse wheel and you can move, okay? It's basic operations in order to move all along the block diagram. So first of all, let's check how Mary or Peter are being generated. So first of all, let's check Mary. Well, for Peter, it goes the same, okay? And the key block that you have here is this event-based entity generator, okay? This event-based entity generator will generate Mary in this port, as you can see. Well, pay attention to the difference of a timed signal, as you can see here, this arrow ending, and on an entity port in here. This is not a signal. This is an entity, okay? Mary, a customer, a car entering a toll road, a patient entering at the hospital, okay? So this will be entities. Can you see the double ending in the arrow? That's the idea, okay? So here you don't have a time signal, you have an entity, an object. That's the difference. So the key difference between SimEvents and all the others, toolboxes within the Simulink environment will be this, as you can see, the entities. Okay, so well, let's go into this block. As you can see, you can generate entities upon a sample time hit from the pod. So as a new sample time appears in an external pod, a new entity will be generated, a trigger, a function call, or the most commonly used in this course will be a change in signal from an incoming pod. Here we are. So every time a signal in this incoming pod changes, then a new entity will be generated. Okay? And this change can be can be a rising change, a falling change, or either. So that means that if here you have a change here in this direction, so a rising change, a new entity will be generated. If you have a falling change, a new entity will be generated, or either. So rising or falling edge. That's the general idea. Okay, so my configuration is a change in signal, but only for rising, as you can see. Okay, so then, because I want a single Mary being generated, that's the reason why here I have a step. Okay, a step at the beginning, as you can see, a step at the beginning at 1 millisecond, as you can see here. Okay, so the final value is not important. You can put a 1, a 10, whatever you want. Okay, that's the general idea. But the important thing is that here you have a step function, because the step has a single rising edge. Okay, that's the general idea. Then here I have a timed to event signal. Why? Because here I have a timed block, and here I have a block that it's based on entity inputs. Okay, so the important thing is that here I have an event-based block, while here I have a timed-based block. So that's why I need, you remember, I need a connection between timed signals and event-based signals. That's the reason of this symbol. You remember, I told you that here I have timed signals, and here we have events that will happen only at discrete times all along the simulation. So here only a single Mary will be generated. Why? Because a step has only a single rising edge. This is configured about a rising edge, and then this conversion will be expected because this is a time signal, this is a block that it's working on events. Okay, that's the general idea. Fine. Then once Mary is generated, this is a path combiner. You can put as many input blocks as you want. Okay, so Mary can income to these blocks now only by 2 different paths. Okay, but you can put here as many as you want. Okay, fine. Then the next block will be Mary studying. So let's go to Mary studying block. This Mary studying block is a single block. Okay, so it's a single server. So it has a single process. Okay, and this service time will come from the signal port T. So the time that Mary will be studying will income from this incoming port. Okay, that's this input port. That's the idea. But you can do it by means of a dialog. Service time, I don't know, 123, 23.6, anything you want to type in here. Then from a signal port T, or from attribute. The attribute will be explained in the next session, during the next session. So now I'm not going to explain the attributes because it's the main focus of the next lecture. Okay, so for today's lecture, signal port, and that's the signal port that will inform this block about how long will be Mary studying. And what's the probability density function? Let's check here. This is the event-based random number. Now it's configured with a distribution that is a uniform probability density function. But you can choose between all these, as you can see. Exponential, uniform, triangular, or Gaussian will be the most commonly used probability density functions during this course, during this semester. Okay, so I ask you for a review of these most commonly used probability density functions. Okay, exponential, uniform, triangular, or Gaussian. Okay, these will be the most commonly used during this semester. Then for this uniform, we have a minimum of 5 minutes because the units are minutes, okay? 5 minutes or 10 minutes. Well, in order to keep things clear, here, this 5 has no units, okay? So simulation time will depend on your interpretation, okay? Will depend on how you understand this simulation time. So here, as you can see, the simulation time is 120, okay? You can understand that these are seconds, minutes, hours, days, it doesn't matter, okay? Well, it depends on your problem. Now, this is 2 hours, so 120 minutes, because all the units in here are minutes. So Mary will be studying between 5 and 10 minutes. That's the idea, okay? But it has no meaning for the simulation software. 5 and 10, they are time units, okay? It's about you, that you need to understand that these are 5 and 10 minutes, okay? There is no place in the simulation software to tell that these are minutes, seconds, hours, days, years, okay? So the idea that's behind this explanation is that 5 and 10 will only make sense when you read the simulation results. Will only make sense depending on how do you understand this, okay? Because here we don't have units. But obviously, all the units must be the same. If here I have minutes, all the blocks must be configured in minutes, okay? Well, here there is a new important thing. Here we need an initial seed, okay? Because this is a random number, okay? The important thing is that this is a random number. The random number generator that's behind this block needs an initial seed, okay? So a first number to work on, okay? That's the general idea. Because at the end, it's a table and the software gets access to this table in order to generate a random number according to this probability density function, okay? So here the important thing is that you can put here any number you want. For example, 1 or 5 or 1, 2, 3, 4, 5, any number you want, okay? The important thing is that here I have worked with the following concept. Here, 1 plus round the addition, the sum of clock. Let's check what's this. Here I have the clock, as you can see, clock. Okay, this is the year, the month, the day, hour, minute, and as you can see here, seconds with a high precision. Okay, so clock will inform me about the exact value for the time right now. If I type again clock, obviously the minute is the same, but this number has changed, as you can see. Okay, so what am I doing? I'm doing the addition, sum of all the clock, and this results in this number, as you can see. Then when I say sum here, as you can see, when I say sum clock, and then I put around this initial seed must be an integer number. Okay, that's why I put the round in here. Okay, and then I add a number 1. You will see this is because when I say this round of this, okay, I get a number. Okay, and this number will be fed in here, but as you can see, I add another number, a 1. Obviously in other block, for example this, I do the same thing, round of the sum of the clock, but I add a different number. In order to what? In order to make this random number being so different than this number. And here I put, as you can see, a 3, here a 4. Okay, so that's the idea. The idea is that here I will have a different number than here, and a different number than here, and then here. And very important, if I run now the model, I will get here a result. Can you see? Percentage of use, 92.16. If I run again this model, if I run again, the result will be different, 94.95. If I run again this model, the result will be different, 92.89. Okay, and if you check at, for example, this plot, as you can see, every time I run the model in here, as you can see, the results will be different. Can you see? The results are always different. Okay, I get different results for every simulation, and that is very important. Why? Because I want to get statistical results. Okay, if you don't put different random seeds in here for every simulation, you will get always the same simulation result, and you don't want this. You want to get different simulation results in order to get statistics. So the general idea behind this is that the random seeds must be configured depending on the clock. So that's why I put round of the sum of the clock, and then I add an additional number, in this case 1, 2, 3, 4, in order to get different numbers, different seeds for every random number generator. Okay, that's the general idea. Well, so now Mary is out of this block. Okay, Mary has finished studying, and then we start the timer that will measure the time that Mary is waiting for the computer to be idle. Okay, because Mary here will acquire the resource, well, calculator, computer. Okay, that's the idea. Mary, in order to get to the next process that is doing calculation, Mary needs the computer, the calculator. And how many calculators 1. Okay, that's the idea. Mary needs a calculator and only a single calculator. Important thing here, the size of the queue. Can you see? 1, because there is a single Mary. Okay, so maximum number of waiting entities, 1, because we have a single Mary. Okay, then the acquisition priority, I will talk about priority later on in this course. Okay, so for today's lecture, we will forget about priority. Fine, so now I start the timer, and the timer tag, because we need a tag name, okay? Because we have several timers in my block diagram, as you can see. And this timer will be named Mary doing calculations, okay? And this timer will be Peter doing calculations, okay? And the important thing, the timer starts when an entity arrives to the block, okay? So this timer will start when an entity comes to this block. But every time an entity enters to this block, the timer must start again, must restart, must continue the counting the time. So in this case, the timer, if the timer has already started, we want to restart the timer. So the timer will begin from 0 every time, will start from 0 every time that Mary gets into this block, okay? Because I want to know not the cumulative time, but the time between this point and this point, okay? Maybe in some situations, you need the cumulative time. All the time in this 120 minutes that Mary has been waiting for the calculator. So if you want this, you must continue, okay? Warn and continue is when you ask for a warning before continue, okay? So restart or continue. You measure from 0, you continue the timer, okay? That's the idea. And then here, obviously, the reading of the timer, Mary doing calculations, while here is Peter doing calculations. And here, as you can see, some information from this block will be sent to a to workspace block. If I click here, this is a to workspace block. So this will be some information that will be recorded in the workspace. Let's check here that in the workspace, here I have the variables in the workspace, as you can see. And these variables, meantime, Mary waiting for calculations, Mary waiting for calculations. So this Mary waiting for calculations comes from here, Mary waiting for calculations. And what's this information? Every time that Mary enters this block, here we'll have the elapsed time. ET goes for elapsed time. Let's double click in here. And as you can see here, the statistics, you can get the number of entities deported. So the number of entities that got out of this block, the number of entities deported with specific tag name, okay? The elapsed time or the average elapsed time. In this case, I use the elapsed time. So every time Mary gets out of this resource acquire block, and then we read the timer, every time that Mary goes out from this read timer, we have a stamp, a time stamp on how long has been Mary waiting for the calculator. So how many times Mary has been through this block? as you can see here, 11 times on the last simulation, okay? 11 times. So Mary has been using the calculations 11 times. And if you want to see the time that Mary has been waiting, here we have the times, okay? And the probability distribution that we have is here for all the simulations. But on the last simulation, we have this, okay? Here we have nearly 10 minutes, as you can see, nearly 8 minutes, and so on, okay? But this is for a single simulation. Well, let's go back here. Then once Mary has the computer, then Mary is doing calculations. So again, a single block, as you can see here, single server block, single port T, and this T will be a probability density function with a uniform shape, okay? Here we have 1 minute, 2 minutes. Why? Because Mary spends most of the time thinking about what to do, and then a small time doing the things. But Peter is the other way around, thinking not so much, okay, and using the calculator a lot of time, okay? That's the general idea behind this. So afterwards, once Mary has finished with the computer, we have the resource release, and this resource release here we release the calculator, okay? That's the idea. And obviously you can choose the resources to release. Selected, so the selected resources, but you can release all the resources that Mary has been using, okay? But here we have a single resource. Well, it doesn't matter, all selected, okay? I strictly prefer selected because you have control about the resources to release, okay? That's the idea. Fine. So then, what about these statistics in here, as you can see? And what about these statistics in here? Well, on the resource acquired, we have sharp N and W. Let's check about what's the meaning of sharp N and W. Here we have the statistics tab, as you can see, statistics tab. And then here we have the number of entities departed, again, the number of entities in block. So this number, this sharp N, will inform us if Mary is waiting for the calculator, okay? So in the resource acquired, if we have here in sharp N equal to 1, it means that Mary is waiting for the calculator. So here we have Mary queuing for computer. So let's check. Here we have Mary waiting, Mary waiting, Mary waiting about 10 minutes. You remember 8 minutes, 10 minutes. Mary is waiting for what? Is waiting for Peter to leave, to release the resource, okay, the computer. That's the idea. And this here is Peter waiting for Mary to release the computer. Most of the times Peter is not waiting because Peter asks for the computer and immediately the computer is available. Asks, but the computer is always idle because Mary is not using the computer at all, okay? But you have here, as you can see, Peter is waiting for a short time, okay, for Mary to release the computer. Here again a short time, and here about, I don't know, 2 minutes, 1 minute and a half, okay? That's the difference of the behavior. Mary waiting a lot of time, Peter waiting nearly nothing, okay? That's the idea. And I take this information from the resource acquired block. Because if Mary is here, I have a 1. If Mary is not here, I have a 0. What about the W? The W is the average wait. So the time Mary is waiting for the computer is measured, and we have the average wait in here. Let's check this average wait. You have here the average wait for the computer, okay, for Mary, and the W for Peter, okay. Let's plot this. As you can see here, this is the mean time. First of all, the mean time is 0 because they are not waiting. Now, Mary is not waiting, okay? Here, Peter is not waiting. As you can see, the values, Mary, the mean time for Mary is moving about 5, 6, 4, okay? While Peter is 0 point something, okay? The key point is that this is a dynamic signal because the computer is calculating the total amount that an entity is waiting for a resource divided by the simulation time, okay? So that's why when Mary was waiting a lot, let's check here, let's go back here. When Mary is waiting a lot, can you see here that Mary is waiting a lot? 8 minutes, 10 minutes, okay? 4 minutes, more or less in here, 3 minutes. Here we have a peak. Here we have a peak, as you can see, okay? This signal is rising so fast because at the beginning, Mary is waiting a lot of time for the computer, okay? And at the end, more or less, it reaches like the steady state value, okay? But as you can see, here I have more or less a steady state value, more or less. Obviously, the most of the time, this signal at the end, the most of the time the simulation spends running, this signal at the end will be like more or less quite a steady state signal, okay? It may be so oscillating, but at the end it will be more or less so constant, okay? And the same goes for Peter, but Peter waits a small amount of time. That's the idea. Okay, so let's now go to the statistics for the resource pool. As you can see here, the resource pool has two statistics, the amount in use and the average utilization. The amount of use is very important because here, the amount of use, as you can see here, the amount of use here is the addition for Mary and Peter, okay? So Peter, as you can see, is using the computer most of the time. Here, Mary is using the computer, is not using the computer at the end, okay? And here you have the addition of these two signals. If you add these two signals, then here we have the result, okay? And as you can see, the computer is idle this time, here this time, and this time. But most of the time, Peter is using the computer. It's so obvious, I know. This is only a simple example, but in your future work, you may build more complex models, as we will do for the next session. On the next session, we will build the emergency stage model. You will see, okay? Well, so now let's check for the last statistic, that it's Mary here doing calculations. Here we have, for the statistics, the number of entities in block. So that means that when you have a 1 in here, means that Mary is using the computer. That's why in this scope, we have the computer use in here. we have Mary using the computer because Mary is in this block, and Peter using the computer because Peter is in this block. Well, the remaining block to be explained is the resource pool, okay? The resource pool, first of all, the name must be given, okay? Calculator, in this case. It's a discrete unit because you cannot have half a computer, okay? That's the idea. And a very important thing is that when Mary has finished using the computer is reusable upon release, okay? If the release is something that cannot be reused again, food, painting, water, or whatever, you must untick this because the resource will be not reusable, okay? That's the idea. But the computer can be used all the time, okay? Can be reused all the time. Then the resource amount will be a dialog one because we will define that there is a single resource, a single computer. But if you have, for example, different number of resources depending on the simulation time, for example, work shifts, different people assisting patients at the hospital, so different number of nurses, doctors, and administration personnel, depending on time, then you must use signal port. And then you will see that a new port, as you can see here, will appear when I apply, it appears a new import in here, amount, and you must give this block the number of resources from this input port, the amount port, okay? But this will not be our case, so resource amount dialog, okay? And obviously the input port disappears, okay? So now that we have finished with all the explanation of this block diagram, we will go to the MATLAB code that allows us to run this model several times and get some statistics out from these simulations, okay? So we will open this, here we are, and we will follow step by step, line by line, all this code. Well, first of all, I clear the command window. CLC is clear the command window. This, first of all, I will ask the user to enter the number of replications, the number of times that the model must be run, okay? So this number of replications will be the input of the user when the user is asked, what is the number of replications? Okay, so then the user enters 100, 200, 150, whatever, okay? Then the model will be loaded, okay? So first of all, I display the information to the user, this message to the user, loading the model, please wait, because it takes some time, okay? And then I open the model, sharing the computer. So at this point, the model is being opened, okay? Well, if you have already opened the model, it takes a small time, okay? But if it's the first time you open the model during this session, it will take a lot of time. So it's very important to give a message to the user, well, loading the model, please wait, okay? Once this instruction has finished, then I display model already loaded, okay? Well, so then I will give the arrays for the calculator being busy, okay, the computer being busy, and then at the meantime, Mary is waiting for calculations, and the meantime, Peter is waiting for calculations, okay? And it's an array full of zeros with a single row, as you can see here, and number of replications. Okay, so I give MATLAB the variables that will gather all the results for all the NR simulations done. Okay, that's the idea. So this, at this point, this is only for preparing the results. Okay, now obviously they are filled with zero, so nothing to do with that. Okay, and then a simple for loop. It's a simple for loop. For and end. Remember that MATLAB is a high-level language, is an interpreted language, so it's not compiled. Okay, so the for loop is typed like this. For this is the control parameter. Okay, this will run an R times from 1 to 1R to NR, sorry. You can be more specific by doing this, as you will see. This is the beginning value of I. This is the increment between 2, 4 iterations, okay? And this is the final value. It's far different from C language, okay? But it's quite similar. The beginning value, the increment, and the final value, okay? Well, the increment can be omitted if it's 1, because by default, MATLAB interprets that this is an increment of 1, okay? But if you want to be more specific, put a 1 in here, okay? Fine. So then, the first instruction here, the first command is set parameters. This is for managing the simulation. I tell MATLAB that this model must be started. This is only for starting the simulation. Okay, this, I will copy this. Okay, if you do this here, if you run this, the simulation runs. Okay, I will show you. I will try to show you as fast as I can. Okay, but here, if you run this, the simulation, can you see that runs? But it's so fast. Can you see 93.64? If I run this, the result is different. Okay, so the simulation has been run. This is a very interesting command because it allows you to start, pause, stop a simulation. Okay, so once the simulation starts, I display running replication number and I display the iteration I. Okay, that's why here in the command window, running replication number 172 till 200, for example, depending on the number I give to the application. Okay, so then I get the status of the simulation. Why? Because I know that these instructions are so fast. Okay, so the computer has no time to finish the simulation. So at this point, if I want to get the results here I get the results from the simulation. Okay, the problem is that this execution is so fast. So in order to avoid the simulation in order to allow that the simulation will be finished at this point, I always check if the simulation has stopped. Okay, so how can I do this? I get the status. So in opposition to set parameter, get parameter, the simulation model and the simulation status. Okay, and the simulation status can be loaded, started, running, stopped, paused. Okay, so while the status is not, okay, not, this symbol is not equal to stop, okay, you can get this symbol not by pressing the Alt key and 126, okay, in your computer, or Alt graphics and this letter in Spanish, okay. If you press Alt graphics and this letter, then you get the symbol, or Alt and 126, because the ASCII code for this symbol is 126, okay? The ASCII code for this symbol is 126. I know in C language, not is this, but here, this symbol is used for a different purpose, okay, in MATLAB language. So if the status is not stopped, it means that the simulation is still running. So I do a small pause in order to let the system stop, okay, and then I get the status again. I get the simulation status, and then I compare. The status is not equal to stop. If it's not equal to stop, so it's running, then I do this again. And I will do this while the status is running, so not equal to stop. Once the simulation has stopped, then this while condition is violated, so then I will continue to this. Calculator VZ for this iteration will be the utilization, but the final value. Let's check what is this utilization. Let's go to the simulation model. Remember, utilization is the util here statistic, that it's the average utilization. Because MATLAB is calculating the average for this variable, I'm only expected to get the final value. So this final value, okay? That's why for this array, this utilization, I get only the final value, because MATLAB is giving me the average utilization. So that's why I get only the final value. And when you want to get the final value of an array, you must type utilization end, because this is the final value, okay? Well, let's go now for the mean time that Mary is waiting for calculations, or the mean time that Peter is waiting for calculations. So let's have a look at these variables. The mean time that Mary is waiting for calculations, here I have the elapsed time every time that Mary is waiting for calculations. Okay, remember the read timer, ET, means elapsed time. So every time that Mary is waiting here for the calculator, for the computer, this timer will measure this elapsed time, okay? So that's why here in the array, I do the mean of this array, but starting from the second sample till the end. Why? Because the first sample, I will show you this in here. The first sample will be a 0, because the first time that Mary enters here, you remember that no one was waiting for the calculator, okay? Because the first time is not being considered. That's why I take the mean, I calculate the mean from the second sample till the last, okay? You can, for example, check this. If you put, for example, a scope in here, I will measure this, okay? And you will see what I mean. When I double click in here, as you can see, the first time is 0, okay? So that's why I calculate the mean value for all the other amplitudes, okay? That's the idea. Fine? And then the key point is that maybe you don't want to use the mean time. Maybe you want to use the maximum value. So that's only a proposal, okay? Because you may consider the maximum time that Mary has been waiting for calculations, okay? Because you want to check the worst case. Or maybe you want to check the best case, okay? So mean time, not the mean, but the minimum time, okay? So that depends on you, okay? Depends on your considerations. If you consider the maximum values, then when you run this, for example, 25 replications that will take a small amount of time, okay? The results will be based on the maximum value of all these values. For example, in this case, this case, this situation. So I will be considering the worst case. So the longest time that Mary has been waiting for the calculator, okay? So let's go now to the last part of the code, that is only the generation of this figure, okay? As you can see here, now because I'm focusing on the worst case, Mary is waiting between 4 and 9 minutes, okay? And Peter is not waiting 0 point something, but the most, or the center value is more than 1 minute, because now I'm focusing on the maximum, on the worst case, the maximum time they have been waiting for the calculator, okay? So finally, I plot the results. How can I plot the results? Very easy. I display we are over, close all the figures, I generate a new figure, and this figure will have 3 subplots. As you can see here, we have 3 subplots, 1, 2, and 3. 3 rows, 1 single column. 3 rows, 1 single column, okay? And finally, the first plot, the second plot, and the third plot. The first plot will be the histogram on the calculator busy, okay? And the number of classes will be defined after the number of replications, okay? For example, if you have 25 replications, you can get 5 classes, okay? So always is the square root, okay? The problem is that if you have 200 replications, you don't get an integer number, so there will be no possibility to build 40.1 classes, okay? So it's 14, sorry, or 15, okay? So here we calculate the floor, okay? This is a rounding function, floor, okay? If you do this floor in here, floor, you will get the integer part, okay? Yeah. So, well, that's the explanation of how can we get the results, displaying the histogram with this number of classes, okay? Important, the labels on the x-axis, computer utilization percentage, mean time, Mary or Peter waiting for the computer.